Okay, I welcome you to this AI ML session this afternoon after lunch. So my name is Eric Harrach. I work for Marvell, where I'm a senior director and I lead the flash architecture team. And I work on flash controllers and other flash storage-related chips and products. Today, I will talk about storage devices for the AI data center. So we have 50 minutes in total. So I'll try to be done in about 40 minutes, and then we have some time for questions as well. So here's the outline of the talk. I'll give a brief introduction into the evolution of AI. I'll touch on AI model complexity, in particular in terms of memory and storage requirements. I'll give a brief introduction into the AI data processing pipeline. Then I'll talk about storage in the AI data center, and then I'll conclude with performance considerations for flash storage and SSDs. So here is a brief summary of the recent AI revolution. It really kicked off 2012 with AlexNet, which was a new neural network-based scheme for image recognition. It really made everyone realize how powerful AI could become. So this really started a whole new class of deep learning research and algorithms. Those algorithms were really used initially for image and speech recognition. Then transformers were invented with GPT-2 and later versions. They were initially used for recommendation models. But then, a real breakthrough came then with generative AI algorithms based on transformer algorithms. That happened around 2020. That really showed then even more to the whole world how powerful AI can become. And, it's continuing in terms of further progress. So then people have introduced multimodal AI algorithms that use text, video, images. They've introduced reasoning capabilities to AI, chain of thought capabilities. And, the next thing is really are two things: agentic AI, so AI agents that can do whole tasks for you. But then there's also a lot of activity around physical AI, robots that are intelligent, that learn in the world. And so as you can see from here, that the complexity of AI algorithms continues to increase. So it puts then also, of course, more requirements in terms of compute memory and storage requirements. So here I would like to give a sense of the complexity of recent AI models. So the initial models were relatively, simple by today's standards. So AlexNet, of course, also had a high parameter count in terms of 60 millions. But as you look at these algorithms here, you can see that state-of-the-art algorithms have more than 1 trillion parameters. However, then if you look at the model size, so if you assume 4 bytes per parameter, you can see that we're talking originally about hundreds of megabytes, more recently about terabytes. So the model size itself, fitted originally into memory, but now increasingly it doesn't, it's challenging to put it all into memory. But these are not huge capacities from a storage perspective. Then the training token size has also increased significantly. And then, of course, from a data storage perspective, the huge amount of data is really in the data that is used for training. So here we're talking about petabytes of data that are being used. And the size for training, data size for training that needs to be used will continue to increase, especially when we talk also about physical AI. So what is the AI processing pipeline? So what are the different phases? There was an excellent talk yesterday by Curtis Ballard. It was the first talk yesterday at 8:30 a.m. So if it was too early for you, I recommend to watch the movie and look at the slides. So it really gave the most up-to-date kind of summary of what this pipeline looks like, in terms of what the processing phases are, what the workloads look like, what the access patterns are in terms of read, write, sequential, random accesses. So here is really a very simplistic view. So first of all, data is being collected, then it needs to be ingested, into this pipeline. So here we are talking about petabytes of data, mostly sequential accesses. Data needs then to be prepared for training, so it needs to be pruned, it needs to be vectorized. So here we are talking about terabytes of data, potentially even more. Accesses are sequential and random. Then during the training phase, the access patterns are highly random, but then there are also sequential accesses in terms of checkpointing data, saving the model state. The data size that is being handled is somewhat smaller at this stage. Then when we talk about inference, these workloads are highly random typically. We're talking about terabytes of data, but what is also now increasingly being used is retrieval augmented generation, so RAG schemes, where essentially vectorized data is used to aid the inference algorithms, and that's where a lot of storage comes into play as well, in terms of many terabytes, even petabytes. And then in the end, data needs to be archived, the data that was used for training, the data that was generated. So here we're talking again about petabytes of data and sequential accesses. So you can see that in general, lots of data that needs to be stored, that needs to be processed. The workloads are quite different depending on the phase, and even within the phase, there are also different sub-workloads that need to be dealt with. I want to give a high-level, overview of training versus inference. When we talk about training, so that's where one large job works on a supercomputer with 10,000 or 100,000 of GPUs. So here the key parameter is bandwidth. So, and also and these jobs can run quite long. So if there's an error in the system, you don't want to lose, all the results at that point. So it's also important to checkpoint the data from time to time to save the model state in storage. Inference, it's very different, especially when we talk about inference in the cloud. Think about millions of users, asking some, tool out there, be it from, OpenAI or Google or Meta or other providers. You have millions of users asking questions, so you have really millions of threads running in parallel. Here, the key parameter is time to answer. So latency is very important. And then, as I said, retrieval augmented generation schemes are also used here. So here we are talking about large vectorized data sets, and that drives additional need for storage. So when the ChatGPT revolution started a few years ago, everyone was asking, what's the role of storage within an AI compute node? And of course, it was known you need GPUs, you need high bandwidth memory, but how much storage do you really actually need? So, what I did together with my colleagues, we talked to customers, of course. We went to conferences like this one. And also I went to exhibitions, to exposition floors to look at the actual AI compute servers. And I want to show, a simplified block diagram of an actual AI compute tray and AI compute rack. So that's, it's an example, but it's one leading rack currently. This is what, in principle, a Blackwell system looks like from NVIDIA with 72 GPUs. And how, is it structured? So you have an AI compute tray or AI compute server. In this particular example, there are 4 GPUs. You have high bandwidth memory. You have 2 CPUs. There's DRAM. And there are SSDs. And actually, there are quite a few of them within one compute tray. You can see there are 8 E1.S SSDs. And then there are NICs, networking interfacing cards, to connect this tray to other racks and also to the external world, and also DPUs that also have networking capabilities, but also offer storage acceleration functions. So that's one tray. But then within a whole rack, in fact, there are 18 compute trays here in this implementation. You also have switch trays that help to connect all these compute trays, in particular the GPUs, all together so that it all acts as one big single computer. So when you sum it all up, so there are 144 E.1 SSDs within one compute rack, AI compute rack. And then the other important thing to look at is what is the SSD to GPU ratio. It's 2:1. So you have 8 SSDs per 4 GPUs. That's somewhat typical. So the SSD to GPU ratio is usually 1 to 2:1 in that range. That's important from a performance perspective, because if you consider that one GPU has 16 PCIe lanes available for performance, that's how you can saturate it. But then one SSD has only 4 lanes, so you have to look at that ratio then to see how do you design these SSDs so that the performance is matched relative to the GPUs, so that the GPUs don't remain idle. Okay, so I talked about an AI compute rack. So there's storage there. As I said, that's local storage within the rack. So performance is important here. But then, of course, lots of data is needed, for that is being loaded into the compute rack from outside. So you have a performance storage tier. So performance is very important here. So that can be storage server, a storage appliance. It's connected to the AI compute rack via a high-speed fabric, typically InfiniBand, Ethernet, or optimized Ethernet schemes, such as Ultra Ethernet, which is a new standard. Then within this performance storage tiers, usually you would use high-performance SSDs, TLC SSDs, or it could also be QLC SSDs if you optimize them for performance as well. And then further removed from that, you have a capacity storage tier. And so the emphasis here is capacity, not storage. So what is being employed here are typically, HDDs, hard disk drives, of course, but then also increasingly also QLC SSDs. And again, so this capacity storage tier is connected to the AI compute rack via a fabric, via Ethernet. But, it could be a more traditional Ethernet scheme there because it's not as performance sensitive. Okay, so how do you connect storage, in particular SSDs, to GPUs and to CPUs? So here I'm showing 3 schemes for local NVMe storage within an AI compute node that's direct attached via PCIe. So the most forward scheme is to connect an SSD first directly to a CPU using the PCIe bus. And then the GPU is also connected to the CPU via PCIe bus. So when you do that, you're limited in terms of how many SSDs you can connect, because it's really determined by the number of PCIe lanes that are available by the CPU for storage. So another possibility is to use a DPU, so to connect SSDs to the CPU via a DPU. So the DPU can aggregate multiple SSDs. So here you can increase the number of SSDs that you connect to the CPU. The DPU can also virtualize the SSD, and the SSDs and also can provide additional acceleration functions. For example, for virtual machine capabilities, for encryption, for compression, if that's needed. And then, a even more scalable approach is to use a PCI switch. So essentially, you connect a GPU and multiple SSDs via PCIe switch to the CPU. So that's the most scalable scheme in terms of increasing the number of SSDs to increase performance and also to increase capacity. Okay, so how about remote storage? So here I'm showing on the left side a compute node. It uses, as I have shown before, CPU, GPUs, PCI switch SSDs. You use a network interface card then to connect that compute node to a network that connects into a storage node. And then on the storage node side, so you would have typically also a NIC and a CPU for all the storage-related stacks, and a PCIe switch then that connects them to multiple SSDs. So you would use typically Ethernet, Ultra Ethernet, InfiniBand for performance storage tier in a so-called east-west network within an AI cluster, and then more traditional Ethernet for capacity storage tier in a north-south network. So how about, you could also replace the NIC and the CPU in a storage node by a DPU that combines them both into one function, as shown here. So how does it all fit then together in an AI cluster, AI compute cluster, and how is it connected to storage? So this is shown here. So first of all, let's start with a compute node. And, as a compute node, think about the compute tray that I showed before. So, you have here, in an example, you have one CPU, you have multiple GPUs, 2 GPUs, for example. The CPU has DRAM, of course, often LP, DDR DRAM. The GPUs have high bandwidth memory connected directly through an interposer. And then all the GPUs are connected to each other using a scale-up network. So that could be PCIe, it could be proprietary schemes like NVLink, but there's also a new standard that was published, UA-Link, that helps to connect GPUs together so that you achieve very high bandwidth and so that everything is cache coherent from a memory perspective. And then, you also have SSDs within a compute node, as I've shown before, and you connect the SSDs via PCI switches typically to the CPUs and GPUs. So that's one compute node. You can connect multiple compute nodes together, again with a scale-out network, which is shown here. And so the scale-out network, as I said before, sometimes it can also be called the east-west network. It's Ethernet, but it really should be an Ethernet that allows for good quality of service, congestion control, low latency. So for that reason, their improved Ethernet schemes have been developed, and there's a new standard, for example, Ultra Ethernet, that addresses this. And then this is all within a compute cluster to connect multiple compute nodes together. And within that compute cluster, connected to that east-west network, you also have remote performance storage. So it could be a storage server, it could be a storage appliance that then connects to a compute node via this scale-out east-west network. And then you have another network, it's called typically the north-south network, that then can connect multiple compute clusters together, or even multiple data centers together. And that also employs Ethernet, and there again, you would have storage there as well, and usually that's then the focus there's capacity, and that's the remote capacity storage that I mentioned earlier. So here one diagram that tries to show everything together, first of all in terms of CPUs, GPUs, memory, but in particular also where does storage sit. So as I said, you have local storage within a compute node. Then you have remote performance storage within the compute cluster. And then even further away, you have remote capacity storage tiers. So this is, another way kind of to show those tiers. I think, we're all familiar with the memory and storage hierarchy. In the old days, it was essentially just SRAM, DRAM, storage. But, more tiers have been introduced over time. And here you see kind of the tiering that you see now in an AI data center. Of course, you have first SRAM within the CPUs and within the GPUs, on chip. High bandwidth memory comes then next. Then you have DRAM, high bandwidth memory right next to the GPUs, DRAM right next to the CPUs. Local storage within the AI compute node, so local NVMe SSDs typically. Then remote performance storage. Often these are also NVMe SSDs, and then remote capacity storage, where you have HDDs or QLC SSDs. So of course the capacity increases when you go from top to bottom, but the latency also increases when you go from top to bottom. And then, here you can see how it's all connected. SRAM, it's on the chip, HBM with an HBM interposer within a package. DRAM usually, uses a DDR interface or CXL. You have PCIe and NVMe for local storage, then Ethernet, Ultra Ethernet, InfiniBand for remote storage on the performance side, and also Ethernet and object storage schemes for remote capacity storage. So, what about how do GPUs access storage? So that's very important. You don't want the GPUs to keep them idle, especially during the training inference phases. So the traditional way is that you have a CPU that initiates and controls everything. So here you can see a CPU, GPU, PCI switch, SSD. So in a traditional scheme, the CPU initiates the access to storage, and then the data flows from the SSD via the CPU back to the GPU. So that's somewhat simplistic, but that's what the main steps are. Here, what you can see is that the CPU is in a path. There's a high overhead due to the CPU, and so it's not desirable for AI. Then an improvement over this is GPU direct storage. So that was initially introduced by NVIDIA. So here, I call it more general terms, CPU-initiated GPU storage I/O. So the initiation still comes from the CPU, as you can see here. But once the CPU initiates the access to storage, the GPU and SSD can communicate directly. So the data can flow directly from the SSD to the GPU. So there's still some CPU overhead for the initiation, but then not for the actual transfer. So it's an improvement over the past. And then, of course, you would like to get the CPU completely out of the picture. So there's also a scheme that has been described for this in 2023. It was a collaboration between NVIDIA and UIUC. And actually, two authors of this paper, they're presenting at 3 p.m. in this session. So I recommend to go to that session. So here in this scheme, which I call GPU-initiated storage I/O, the GPU initiates the access to storage, and also the data flow goes from SSD to GPU directly. So there's no CPU overhead. So that's the most desirable scheme, for AI workloads that are GPU-centric. So I want to talk now a bit more about SSDs and SSD performance considerations. So in the past, when we talk about data centers, SSDs adopted the next generation PCIe interfaces later than CPUs because not that much performance was needed from the SSDs. However, with AI workloads, SSDs are in a critical path, and they're really the slowest link within the AI processing. When we talk about the compute node, the compute cluster within that node and cluster. So what we're seeing now with AI and AI data centers, that AI data centers are really driving the adoption of next generation PCIe SSDs. In the past, SSDs were typically designed to saturate sequential performance and also to separate 4K byte random read performance. However, with AI workloads, the access patterns are much shorter, smaller than 4K bytes. And that's in particular the case for inference workloads. So what does that mean? So here, you can see a GPU that is connected to SSDs via PCIe or fabric, as I've shown before. So when we talk about, and a GPU has 16 lanes that could be used for storage. And when we talk about Gen 6, what do 16 PCIe lanes mean? It means 128 gigabytes per second raw bandwidth. But PCIe has overhead, so effectively 110 gigabytes per second are available for 16 PCIe lanes. So in the past, we looked at 4K byte performance. So what did it mean for 4K byte performance? That you need about 27 million IOPS for storage for 16 lanes. When we talk up however, an SSD has just 4 PCIe lanes, so you divide it again by 4, so you end up here with 6.7 million IOPS. So in the past, for data centers for Gen 6, in order to saturate performance, the SSD needed to achieve about 6.7 million IOPS, for 4K byte accesses. But now with AI, since the access patterns are smaller, if you look at 512 byte accesses, the IOPS requirement increases by a factor of 8. So for 16 PCIe lanes, 26.8 million IOPS becomes 215. When we talk on a per SSD basis, 6.7 million IOPS turns into 53.7 million IOPS. So that's really, the challenge now for storage for AI. How do you improve the IOPS capability by a factor of 8 so that you saturate the link towards the GPUs? You can saturate the performance, of course, by building a high IOPS SSD, and I'll talk about later. Another option is to use more SSDs, multiple SSDs. So what does that mean? So here this table shows as a function of the PCIe generation, what the IOPS target is per GPU. For Gen 6, as I said before, it's 200 million IOPS per GPU. So if you look at typical data center SSDs that are optimized for 4K bytes, they operate at, or they max out at about 6.25 million IOPS. I mean, it's really 200 million IOPS divided by 4K bytes, so you end up at 6.25. So how many of these drives do you need to get back to 200 million IOPS? You need 32. So with 32 state-of-the-art drives, you can saturate the link for GPUs. So it's quite a few drives. However, if you were able to build one high IOPS drive that achieves 50 million IOPS, as shown here, you can do that with just 4 SSDs, and the 4 SSDs fill in, this one PCIe slot that has 16 lanes. Of course, you can also try to do something in between. Let's say if someone builds a 12.5 million IOPS drives, you just need 16 SSDs to saturate the performance from a GPU perspective. And that's really, the challenge now, to find the right trade-off. Of course, it's very expensive to build a very high IOPS SSD. On the other hand, you can put multiple SSDs together. It's somewhat simpler from a development perspective, but if you use more SSDs, then you also burn more power. The cost also goes up then in terms of the bill of materials. So the question here is really, what's the right trade-off in terms of cost, power, time to market? So what is needed to really develop a high IOPS SSD? So I'm showing here the block diagram of a SSD controller. So on the host side, you have a PCIe interface. On top of that, you run the NVMe protocol to talk to the host. There are CPUs inside the SSD to do all the processing that is needed, for example, for the flash translation layer, to process the host commands, to drive the NAND interface. There's a DDR interface that connects to DRAM, and that DRAM is needed really to store the flash translation layer tables, then logical to physical mapping of pages. Then there's a flash controller that talks to the NAND, and there's a NAND interface. So what needs to be looked at in terms of improving for high IOPS, to get to high IOPS? First, on the NAND side, the NAND media. You need to look at, how can you make it faster? How can you reduce the read time? There are different trade-offs there. NAND usually now has 3 bits per cell or 4 bits per cell. So that it's called TLC or QLC NAND. So you need, for this type of NAND, the sensing of the voltages. It requires multiple steps, which increases the read time. So you could really speed up the read time by moving to single-level cell schemes where you just have 2 voltage states. Then you can also look at the page and plane architecture. I will show that later. Then on the SSD controller side, current SSD controllers are really optimized for 4K byte performance, as I've shown before. If you need to improve the IOPS by a factor of 8, you need to think about, how do you need to scale up the processing capability of the CPUs? Do you need to add more hardware acceleration into the controller to offload firmware, to get to your target performance really in a power-efficient manner? And then on the host interface side, so the host interface is really optimized now for 4K byte pages, accesses, but also, 512 byte sectors also have been still around. But if you also have accesses that are even smaller than 512 bytes, you need to look at the host interface and see what improvements are there needed to reduce any overheads that may be there that impact performance. And then we also need to look at the form factors. 8 times more random read performance will increase the power. So what does that mean in terms of the form factor? So I'll dig into some of these items here in a bit more detail in the later slides. So first of all, I want to talk about the NAND side. So, what determines really read performance on a NAND side? So the reason why SSDs achieve such high performance, especially also for read, is that because there's a lot of parallelism in the system. So you have an SSD controller NAND interface. So first of all, it connects to multiple NAND packages. So it has multiple NAND channels. So here in this example, I'm showing just 2 NAND channels. But typical data center SSDs actually have 16 NAND channels. And then each of the NAND channels connects to multiple NAND packages, as shown here. Within a NAND package, you have multiple NAND dies that can be addressed. And then within a NAND die, you have multiple planes, and within each plane, there are multiple pages. And so what determines the read performance is really that, is the question, how many pages can you read in parallel outside the NAND? So first of all, how many pages within a NAND die can you read in parallel? And then also how many NAND packages and NAND dies per package are available. So these are key factors for your read performance that need to be looked at in terms of improving the random read IOPS. So let's talk a bit more then about those parameters. So of course, you want to improve the random read IOPS, so you need to improve the read time. So you need to look at page size. As I said, within each NAND, you access the NAND by addressing pages. So so you need to improve the random read performance. One consideration is to reduce the page size. To improve the read time. But then, that has, of course, issues in terms of designing new NAND. So another possibility is not to necessarily reduce the page size to really a small size, but to reduce the read unit size. You still have a relatively large page, but then you just read a portion of the page out. So that can also help with your read time. Another parameter is code word size for the error correction. So in the past, there has been a trend towards going towards larger code word sizes, because with larger code word sizes, you get more efficient error correction schemes. But now, actually, when you want to improve the read time for high IOPS SSDs, you need to look again at going towards smaller code word sizes in order to improve the read time. But it has implications in terms of error correction capability and also the efficiency of the error correction codes. And then, as I said before, one key kind of factor in terms of improving read time is to move from TLC NAND to SLC NAND. So we're instead of having 8 voltage levels within a NAND cell, moving towards 2. So that also improves read time significantly. I talked about read parallelism. So in terms of improving read performance, you need to look at how many pages can you read concurrently within a die, how many dies do you have per channel. Then a key factor is also the NAND channel. What's the bandwidth of the NAND channel? So you have to look at the NAND channel speed. You have to look at the number of NAND channels. You have to look at the efficiency of the NAND channel, because the NAND channel, similar to the PCIe link, has overhead, command overhead. So you have to look at the efficiency of the NAND channel and look at whether further improvements are necessary. And then, as I said before, we also need to look at the SSD controller and the IOPS capability of the SSD controller, especially in terms of the processing and hardware acceleration capabilities. So here I wanted to show the SSD performance and NAND speed, in the past, and also what we can see in the future. So when we look at Gen 5 and Gen 6 here, so we were talking about 16 or 32 gigabytes per second throughput on the host side. From a 4K byte IOPS perspective, it was 3 or 6 million IOPS, as I said before. So the NAND speed for Gen 5 drives, that was typically 1,600 mega transfers per second. Gen 6, it's about 3,200 mega transfers per second. So what you can see is, of course, as the host performance doubles, also on the NAND side, the NAND speed also doubles, so that the throughput of the host and NAND are matched to each other. So when we look now at Gen 7 and Gen 8, and people are talking about that already for AI, we expect the doubling of the speed of each generation. So it also means that the NAND interface needs to double. So here are the extrapolated numbers. And that, of course, has quite, it's a challenge, on the PCIe side, but also on the NAND side, to develop these high-speed NAND interfaces, from a signal integrity perspective, but also from a power perspective, because the circuits, you have analog circuits. Then on the interface side, the power doesn't scale as well as with the digital circuits. And then, when we look about small I/O sizes, so in the past, when NAND was being addressed, it was done in terms of page sizes that were multiples of 4K bytes. But now when we go towards accesses of 512 bytes, the overhead within the NAND channel becomes more significant. You have overhead due to the commands. So when we need to look, the industry really needs to look at how to optimize the NAND interface, the NAND efficiency, the NAND command overheads for high IOPS as applications. So here I wanted to show, IOPS as a function of number of dies. So as I said before, the read performance is, a factor of the number of pages that you can read concurrently. So in the end, a key factor here is the number of dies. So you can see, and I'm showing here two scenarios. So now one is for TLC flash, and one is for low latency flash. So as you increase the number of dies, the IOPS go up, the random read IOPS go up. But at one point, you hit the limit of the NAND channel, so which is given, by, as I have shown before, the number of NAND channels, the NAND interface speed, and the NAND efficiency. So with the low latency flash, if you are able to significantly reduce the read time of the NAND flash, you get a steeper slope. So essentially, you can achieve this channel limit here earlier. So in other words, you need less dies to saturate performance. Or also, again, in other words, you can saturate performance with less capacity. So I guess, and that's a key trade-off. So you can use TLC, traditional flash, to get to high IOPS, but you need a lot of, in the end, you need more capacity than what you would need otherwise with low latency flash. On the other hand, low latency flash is not really widely available, so it takes also significant cost for the NAND makers to develop low latency flash. So, as I said, there's a trade-off here in terms of the from a cost perspective and also from a capacity perspective. So I wanted also to spend a few words about form factors. So here you can see, all the various form factors for the data center, EDSFF form factors that are out there. When we talk about E1 form factors were really optimized, developed for high density applications. You have E3 form factors that were optimized for performance and also capacity. And then there's a new form factor, E2, that really targets nearline storage, for high capacity QLC SSDs. I'm showing here also the typical capacities that are available currently, or have been available, last year up to now for these different form factors, just to give you a sense of what the capacity points are. But here, my key point here is really that the power. So the SNIA small form factor spec had recommended power numbers for these different form factors, and the industry tried to stay within those power limits. In particular, the industry really tried to stay within 20-25 watts for the SSDs. However, when we talk about high IOPS SSDs, the performance goes up by a factor of 8. So the question is really, what power targets can we design for? Then what cooling should be used? So people have now started to talk about liquid cooling for SSDs. We need to talk also about what should be the dimensions, for those high IOPS SSDs. Where would they sit? And also, what are the targeted capacities? So, I've raised quite a few points. What I want to say is that, there's really room for standardization so that we don't have, different proprietary solutions. It's not cost efficient. Ideally, the industry comes together, to form standards so that we all develop products, that are similar in terms of the key characteristics. So I've listed here a few standards that are relevant. Of course, SNIA, the organizer of this conference, has a key role when we talk about small form factor definitions. If there are any implications on form factors, if we need new form factors. But then also SNIA started a new effort called storage.ai, also to look at all these different aspects to define standards for storage. And then, of course, I want to highlight also the NVIDIA effort called Storage Next. So that's an NVIDIA-led effort to define storage for AI, and that's an effort that is somewhat closed under NDA. And yeah, I mean, that really concludes my talk. So I have a few minutes for questions, I believe. So I would like to open the floor. Yes, please. And there's a microphone here, but otherwise I can repeat your question.
What drives the need for random 512 byte data? Is there really no locality in that data that you would have coalesced in order to read really random 512?
Yeah, so the question is what drives the need for 512 byte or smaller IOs? And here, I think AI kind of data centers operators, NVIDIA are in a better position to, and other AI kind of players in the space in a better position to answer the question. But it has been reported when you look at AI, cloud center kind of providers, they have provided data, that, and they're saying actually, it depends on the workload, but there can be a variety of exercises. It really depends on the algorithm. It doesn't have to be 512 byte. It can even go down, to a few bytes of data. But I maybe recommend the talk that comes later at 3 p.m. here in this session. You may get more color on this. Any other questions? Okay, and I think we're almost out of time, but okay, then thank you.